let's get started. Let's see what we want to talk today. So last week, I didn't know you had those things in other classes. You always can tell me if it's something. Just can tell me. Okay, this is. For okay, last few weeks we talked about different method of processing observations. We learned some algorithm that dealing with data. We call them data-driven algorithms. These methods, like neural network, for example, working with data, learn from data, and if something else as an input coming similar to data, not necessarily those data, like unseen data coming, still can make wise decision. We learned about that. We learned neural network, deep learning, deep neural network, and convolutional neural network that were perfect for two-dimensional and spatial relationship features in the picture. That was great. But as I explained, the problem was two problems for those kind of perception. The main one, you tell me. What was the main problem of neural network? Anything? It was perfect, no problem. No, it was some problem.
Overfitting.
Overfitting. Awesome. Overfitting was one of the big problems. Overfitting, another problem.
It's computationally expensive.
Computationally expensive in terms of learning. Yeah, but yeah, that's correct, but it's not the one that I want to emphasize. Any other things?
It's based on prior data.
It's based on prior data. Based on prior data. No, we can't say that's a problem. The main problem was, I mentioned that we can use that for some specific task, like the task that's very safety critical systems. What was that problem?
Oh, it's not explainable.
Explainable. Explainability. It's not explainable. It's not mathematically, even though we tried a lot, but still, because of those nonlinear activation functions and lots of layers, it's not explainable. If you get, if you predict something using neural network, you can't explain it why. But it's fine, it's correct mostly. It's not explainable. So this overfitting and not explainability actually open a new way and algorithms to see how we can combine with neural network. We don't need to put that away. We can combine the other methods that are more explainable. And today we want to talk about something that is explainable and is a basic of most of other methods like Kalman filter and is explainable, the things that we want to start. We have 1 week and we want to talk mostly in this week regarding to that as much as we can because it's broad, but we're going to focus as much as we can to do a couple of applications of that. This method deals with uncertainty. Very general. You can implement with that so many things. And you can combine it with neural network and can cover so many other topics. Like, for example, I wanted to talk about Kalman filter, but I said, why talk about Kalman filter? I can talk something broader that Kalman filter is part of that. And that's actually called variable-based models and Bayesian inference. Okay, it's all probability. It's all probability. So the one that is, I didn't mention the name of that here. I should, but I can write it here. So that's called variable-based models. In perception and machine learning and AI is called variable-based. Variable-based method. Because we want to talk about the software methods. This is the software method. And Bayesian inference. We're going to talk about this today. We're going to start talking about it. We're just going to introduce that because it needs lots of preparation. Especially we need to know some probability rules. Not that much. We're not going to go too deep on that. We're not going to focus in the mathematical part, but we mostly going to focus in practical use of that. So variable-based models. Why variable? We can see. And what is inference? Again, we're going to talk about it. So let's see what we can get from these variable-based models and Bayesian inference, and later Bayesian the network of Bayesians, and factor graph. It's a graph of factors, that factors are Bayesian, and we are going to the new world that is called Bayesian world. This Bayes, Thomas Bayes, is British mathematician, and he did amazing job regarding to what we know right now as like machine learning. In terms of machine learning, probably he didn't think about that in that time. But right now, the basic of most of predictions and machine learning and AI is based off Bayes theorem and Bayesian rules and things. So we're going to talk about that today. Okay, let's get started. Oh, it's in two parts. Actually, let's bring it up. Okay. What is the goal in probabilistic perception? So we want to get some information from the environment regarding to robot. We need to predict something. We need to estimate something. So the main point is prediction. And prediction is noisy. Because why prediction is noisy? Because environment is noisy, sensors noisy. Nothing is certain really in this world. Maybe most of the things not certain. And so we need to know some probabilistic methods for perception, that when we are dealing with an environment that is not certain, we can use those methods. And the method that I want to talk today is a probabilistic perception. It's going to tell you how you can make decision in a world that is not certain. So we already talked about data-driven models, data-driven models like neural network. It make decision based off data. So yes, actually, that's one of the problem of that, because if the data is not proper and is biased, probably decision gonna be biased. The decision not gonna be wise and good and correct. So it's data-driven. But this is what we have. Data is what we have, the only thing that we have. But if this data get better and better, decision becomes wiser and more precise to reality. And another problem is lots of data. And these data sometimes too much and make model to react weird, that we call that overfitting. So we are feeding the model too much and sometimes even learn noise, learn the things that not supposed to learn. Instead of learning, for example, patterns, learn everything that we feed them, they learn it. But those data are not certain. The data that we feed neural network, for example, sometimes they have some uncertainty on that. But we don't consider that uncertainty properly. That was a kind of problem that we were dealing when we were working with data-driven methods or models. But what else we have? The other things that we have is actually using some probabilistic methods. In probability, we have something called actually conditional probability. So instead of finding certain things, let's find probability of things and then maximize it. Maximize that probability. And finding that unknown with maximizing that probability. So this is the method that the method that actually works in probabilistic perception. So in probabilistic perception, instead of estimating or predicting something directly, we are finding probability of that given whatever we have. So it's a conditional probability. So this kind of probability is not certain probability, it's conditional probability. We say, okay, probability of being a robot being here is, for example, this is based off where was before, and with it's based on previous state, for example, and other things around. For example, that obstacles, whatever we had around, and also is depend on where we want to go. So that's actually good to mention. Like, however, I don't have a space in this page, but I'm gonna mention it somewhere. So anyway, this means conditional probability. We're gonna talk about that today. But again, before starting about probability stuff and talking about some rules and math, let's see what is the big picture of all of perception. All of perception and AI and machine learning is actually based off, probably you have the picture there, but I'm gonna draw some part of that. All of these algorithms are based off, we can fit them in this space. We can move from deterministic methods to a stochastic And some algorithms are deterministic. They don't have any uncertainty, like for example, searching, for example. Some algorithms are very atomic, just certain for a specific task. Some algorithms are factored, based off different factors acting. And some of them are very structured. Also about data, sometimes we know about the system. I mean, we know parameters, for example, or parameters unknown. In this space, so we can say, okay, we have uncertainty, we have atomic and structure, and we have known and unknown. So this is regarding to parameters, how much you know the parameters. Parameters of model. Okay. So yes, generally we want to model. We want to model everything. And even the perception that I'm talking is the result of that model. So modeling means you are mathematically, you want to simulate the world with some parameters. Those parameters sometimes unknown or known. This model is sometimes certain, make decision 100%, or is uncertain. Sometimes give you output and also give you some distribution around it. Say, okay, this value is the output, but there is some variance or covariance there that's showing uncertainty. And also methods sometimes are very specific, sometimes are structured. So based off this space, we can see, for example, if you know parameters, you can do searching to find your solution. How searching works, most of the time using a tree. You are a start, for example, you want to find the best path that robot goes outside. You say, okay, go right. If the right, for example, is open, you can go. But if it's not in, you can just do if and else, and then, you can just make a search tree and have all the options in this tree and find a path to find how, for example, from your position going outside. This is called search. In this method, you know enough information. You know all of this information. For example, this W1, you know this W2. All of these parameters are known. This is called search. Like many years ago, they were using this method for perception. There is no uncertainty there, is very certain. And easy, it's not difficult. Later, other methods introduced, like Markov models or Markov decision model. Markov decision process. Markov decision process. Markov decision process is actually basic of reinforcement learning. Markov is one of the other actually mathematician that did lots of work in terms of robotics. And Markov, any phenomenon that is just dependent on previous state, not past, called Markov. If you make decision just from last minute, not before that, that kind of decision making is a Markov decision making. You can have Markov process. Anytime we are talking about process means something in time, changing in time. It can be Markov sequence, for example. It can be Markov model. We have different Markov model, like hidden Markov model, visible Markov model, Markov decision model. Markov decision model is another one. And also we can have, and Markov decision model is a basic of reinforcement learning. Is amazing topic. Markov decision process. Okay, anyway, this is when you know enough about the model, you have variables, you know enough, but is not certain, is uncertain. Uncertainty can be modeled in Markov decision process. What else we have? We have Bayesian methods or Bayes nets that we want to talk today. Bayes nets. When I'm talking about nets, Bayesian formula can be actually fit in a graphical shape. That's why we call it net. It's like a network. We're going to talk about that. What else we have here? See, we are in that space, in that plane, that everything is noun, variables noun. We also have logic-based things. Logic-based things is just very certain if and or, XOR, these kind of things, you know, like a flow chart. And also we have even more first order logic is going so structured. First order, that is working for very specific task. Okay, so we have this, and we have connection between them too. What that means, it means, for example, Bayes can use logics as well, or Bayes can use, for example, MDP as well. Okay, so this is all the algorithms that exist when you know the model enough, when you know these parameters. But how learn these parameters? Using data. That's the place that we need to make it 3D. We're going to go in this direction up. In here, we have learning, for example, neural network. We have reinforcement learning. So here, based off the data, we can learn some stuff, but still they are connected, like neural network or reinforcement learning can be connected to this, can be connected to that as well. So this diagram shows us how these models can actually communicate to each other and how they are related, and based off your application, how you choose them. If your application, for example, is not a stochastic, why you use, for example, I don't know, Markov decision process or Bayesian nets. Or if the parameters is already given or noun, why you use, for example, neural network. Okay, so this is just a general view, a big picture of all the perception in AI, machine learning, robotics, and yeah. However, we can have more of this, but this is the general methods. If we have more methods, they are just a part of those, for example. Okay, so let's clean this up and show you the better picture. So that's the actually showing these relationships. Okay, so I wanted to just start, give you a little big picture, and then go for probabilistic perception. For probabilistic perception, we need to know some probability for sure. The things that we want to talk today is joint probability. We want to define what is the joint distribution or joint probabilities, marginal and conditional. Okay, And we have an example. Here we have a table. This table is actually in discrete space. Actually, distribution can be shown with a table. In this table, we have this showing probability of sunny and rainy. It's like a weather condition. So we have S for sun and rain, R for rain. And we say 1 means if it's sunny, 0 means it's not rainy. And if it's R is 1 means it's raining. So we define all the possibilities. We can have sun and rain. We can have just sun, not rain. We can have not sun and rain, and all of possibilities. And we put some probabilities for them. Even, for example, having sunny and rain normally is 0, but we put some probability for that as well. 0, 0, 2. The first is joint distribution. Joint distribution actually showing probability of happening. Okay, before that I need to define some stuff. Okay. First of all, we need to see what is random variable. Variable. Any idea what is random variable? You tell me. Is a kind of variable. But what kind of variable? Random. Okay. So yeah, if I want to define random variable in probability class, I'm not gonna say that. It has lots of stuff behind. But for us, is okay to say any variable that is not certain and it has some distribution. When I'm talking it has some distribution, it has some method of computing noise around it, uncertainty around it. Like, for example, I'm saying it's Gaussian. It means, for example, in Gaussian, it means if you are here, for example, the noise around it is around the mean. If that point is the mean, because Gaussian is like this, and here is mean. And as you can see, probability is always higher close to the mean. That makes sense. If you are here right now, probability of being close to this area a little later is higher. So this means it's Gaussian. So Gaussian probability is the main one and very important one. That's called random variable. So random variable is the kind of variable that is not certain and it's actually probabilistic and it has some distribution. We also have random vectors. Random vector. If random variable is x, for example, random vector can be a vector of random variables like x and y, x dot and y dot. We use it a lot in dynamic and in robotics. Let's go more. What about random process? We also have random process. In random process, we add time. So x is base of time. In discrete, we call it k. And yk, x dot k and y dot k. Let's just constant velocity, for example. K means time slice. In time slice 1, in time slice 2. We don't care about that period. Like, for example, can be a second, can be millisecond, can be nanosecond, whatever. Okay, that's random process. Okay, what about instead of time, we go x, make it a function? Random function. What that means, like we have y of x. Maybe instead of y, don't mix this together. Like for example, let x of u, not time, anything, input. Y of u, x dot of u, y dot of u. The function is random. The distribution is over a function. It's very similar to random process. So in random process, you have like this. This is the process in time. But this is also called Gaussian process. Right now it's called Gaussian process. When you are randomizing in a function, it's also called function optimization. It's very advanced. It's actually, this Gaussian process is kind of competing neural network and is explainable. Gaussian process. It's amazing. I'm not going to go deep on that, but it's another topic of perception. Okay, so I said all of this to just talk about the random variables. So they are all start with these random variables, a variable that is not certain. And when you have multiple of them close to each other, they make joint variable. When we are saying, for example, probability of sunny and raining, it means probability of, for example, in this case, sun be 1, and for example, rain be 0. So this means probability of a joint probability. So we're going to take a look at the table. See, for example, probability S is 1 and R is 0 is 0.7. So that's a joint probability. Okay. It's already given based off that table. So the probability of, the joint probability means probability of multiple. It doesn't need to be 2, it can be many, as much as you have. That's joint probability. Let's clean this up. Another one that we have is a marginal. We need marginal too. Marginal distribution, if we have multiple variables, sometimes we are interested to one of them. And we want to get rid of the rest. We say, okay, we have this distribution in this table. We have all of them in this table, but we just want to find probability of sunny. What is the probability of S is 1? In this case, we're just going to check where S is 1 and add them up. Regardless of rain, we add them up. So in this case, it's like probability of sum of S and R. If we just base off the R. So in this case, it is 0.7 plus 0.02, for example. So that's called marginal distribution. So let's clean this up again. So in marginal, we want to get rid of the other variables. We want to remove those variables, and we just want to concentrate in one variable. That's called marginal distribution. We also have conditional. Conditional is the main one. Conditional is that when you have some information already, for example, you have multiple colorful rocks, for example. For example, three different color rock in a box, and you accidentally take one, and it's red, for example. So this red is already taken out of the probability box, so you can get rid of that. So that's why probability of, for example, sunny given rain is probability of sunny and rain divided by probability of rain, because we already know it's rain already. When we are saying probability of sun, if already rain, Because we already know about range, so we remove this from the probability. So this is the formula for conditional probability, but this is not still the main one. The main one coming later, that is Bayesian. Okay, but before that we need to see what is inference means. Inference means when we are talking about probability, sometimes some probabilities are more important for us, and we want to find those. So computing probability of some specific variables that are not unknown, based off other given information called inference. So inference means understanding some unknown variables based off the known variables. Like for example, in robotics, we do that a lot. For example, you want to see if the trajectory of robot, for example, this is obstacles. And this is robot, this is source and destination. And robot wants to find this path. Let's call this path theta. Probability of this path or trajectory. Path and trajectory are different in a dynamic. So we want to find probability of theta given what? Given, for example, source, destination, and obstacles. Maybe we can add more, but this is enough. Based off source and destination and obstacles, you can find the best path. Why? Because based off these obstacles, you can find, we call it, actually, signed distance field. Signed distance field showing in this sign, those circles that I draw, showing signed distance field. Like for example, here, signed distance field showing the closest obstacle to that. We make this field and we make decision. Okay, let's just finish this one and we make it a day. So this is inference. So inference means finding some unknown. Those unknown variables also called latent variable, latent. So the condition is based off the things that we already know. And inference means the one that we don't know and we want to find. And sometimes we marginalize out some of the other variables. Okay, so this is the robot that I explained already. Okay, so that was just probability inference. Okay.